My name is Kadek Ananta Satriadi. I'm a PhD student at Data Visualization and Immersive Analytics Lab. I will be presenting a research project that I have been working on with my supervisors. Our research focuses on multi-scale visual explorations of geospatial data. This is an example of visualizations of earthquake dataset view at global level. Here, we can clearly see the distributions of the earthquakes around the world. The explorations of geospatial information often requires inspections of multiple locations across large areas, viewed at different scales. Multiview techniques such as polyzoom arrange multiple map views showing different locations and scales. Although multiview technique provides solutions for complex visual explorations, the nature of 2D display limits multiview technique scalability in view count and size. Consequently, to focus on specific views, we need to either hide or reduce the size of other views. In immersive spaces such as virtual reality, users can freely place and orient maps in the 3D space. We envision immersive multi-view map, an immersive interface that allows users to create large hierarchical maps and arrange them freely in 3D space. This is an example of exploratory implementations of immersive multi-view map for earthquake dataset. A large overview map is provided, simulating large display wall. We see immersive space as an opportunity to extend multi-view map techniques. To create a child map, the user defines a region on the parent map using slicing metaphor. Then a map pops out. The user can grab newly created map and arrange it freely in the workspace. The child map and parent map are visually linked using a curved line. The user can also get the detailed on-demand information about a specific point or perform local explorations with panning and zooming. Slicing another map creates a series of hierarchical map views, and of course, the new created child map can also be arranged and resized freely. With the immersive multi-view map system, the user can create a large number of hierarchical maps. To our knowledge, our research is the first attempt to explore such an immersive system, and therefore there is very little design guidance to follow. In this research, we are interested in understanding users' map arrangements in immersive multi-view maps environment. To guide the future development of immersive multi-view map systems, we designed a study to observe how users arrange multiple maps in 3D space. We conducted an observation study with 16 participants. We provided multiple maps in 3D level of scales with a total of 24 maps to be arranged in virtual reality environment. To encourage the emergence of variety of layout strategies, we provided participants with 5 consecutive tasks that simulate various multi-scale map interaction scenarios. We analyzed all 80 layouts created by all participants using qualitative approach. What we see here is the simplified versions of each layout created by participants. We grouped the results and findings into 3 main categories: layout geometry, overview detail relationships, which shows positions of child maps relative to their parent, interactive strategies, which shows the most common strategy used by participants while performing the task. Spherical cap is the most common geometry, followed by spherical layout, which uses the 360-degree space around the user. Planar layouts are rather flat layouts and only found in the initial naive layout and the final general layout task. As per overview detail relationships, most participants tend to arrange child maps around their parent without occluding it. This creates a central window arrangement. Other notable layout is coordinated arrangement, where child maps are aligned next to their parent. There is a rare case of occluding layout where participants stack child maps on their parent. We observed 2 types of interaction strategies. Participants with layout preserving strategies did not move the map during the task. In contrast, layout changing strategy relies on moving and grouping maps in space. This indicates the need for automated layout and manual layout authoring tools. We then revisited our exploratory implementations and created automated layout tools. With this panel, users can change layout geometry, map size, and locality, which is the distance between the child map positions and its origin on the parent map. This clip demonstrates the automated layout geometry functions. The flat icon represents planar layout, while the circle represents spherical or spherical cap, depending on the locality value. With the layout panel, changing map size and locality can be performed easily as shown in this clip. Setting locality value to minimum will place child maps around the border of their parent, creating a central window arrangement. To gain users' responses to these advanced features, we conducted user walkthrough sessions with 8 participants and provided automated layout tools as well as more advanced interaction modes. We found that the provided automated layout tool influences users' layout preferences. We also found that participants chose a wider variety of layout geometry, with more percentage of participants prefer planar layout than what we found in the first study. Interestingly, we still found layout changing strategy used by participants despite the provided advanced interaction techniques. In summary, our research focuses on understanding users' generated layouts to inform future designs of immersive multi-view map systems. We conducted observation study and found distinctive layout and interaction patterns. We then revisited our exploratory implementations, created more advanced layout tools, and gained user feedback through user walkthrough sessions. We hope that this research encourages future research in the immersive multi-view map system. Thank you.